An instrumentation differential amplifier is discussed in this circuit design example. This is implemented in two stages. Stage 1 is a core differential amplifier with bipolar junction transistors. As you can see, the input voltage is applied to the base of these two BJT transistors. We also have a current source bottom circuit to provide the DC current, and then we have the final instrumentation amplifier at the end of the circuit that converts the current to the difference voltage or differential voltage. So let's see how this circuit is working. We want to see the operation of the circuit intuitively, and also at the same time we want to show that the output voltage at the output of the circuit at this node at the output of the op-amp is equal to approximately 2 times R2, the resistor in the feedback loop of op-amp, divided by R1, the resistor that is connecting the emitter of the two BJT transistors. So it's a simple formula, but it's an interesting operation. Okay, so let's start with the DC bias quickly. So we have a combination of two bipolar junction transistors in a sort of like a VDLAR, let's say current source style, but basically using a Zener diode as a reference. We have 2.7 volt Zener diode. The nice thing about that 2.7 Zener diode for this circuit is, for example, if you look at what options available, so here is the Zener diode, the look of Zener diode, and for example, there are many providers, but if you, for example, look at the Vishay as one of the providers of, let's say, Zener diodes, then you can see that if you go with, say, 2.7 volt Zener diode here, so I'm talking about, let me increase the size. I'm talking about the part number 185223, 2.7 volt. Of course, the bias current is anything between 0.25 milliamp to 20 milliamp range. And the nice thing is for the coefficient, temperature coefficient, you see that it is on the order of, say, for 2.7, it's on the order of negative 0.085%. So that means the actual formula with that, it means the actual formula for the Zener diode voltage, so VZ nominal. So VZ nominal is equal to 2.7 volt, and then 1 minus, because it's a negative temperature coefficient, and we are talking about 0.85 as was reported, divide by 100. So this is the actual nominal voltage times temperature, of course, temperature being the absolute Kelvin, so absolute temperature. Okay, so with that in mind, if we have, let's say, a delta T of, or increase of 1 degree and 1 degree Celsius or Kelvin, then we end up having effectively the delta V nominal Z will be equal to 2.7, of course a negative number, so negative 2.7 times 0.085 divided by 100. This is roughly on the order of, say, minus 2.5-ish, minus 2.4, 2.5 approximately, and we are talking about millivolt per degree C or per degree Kelvin. So the nice thing about this number is we are saying effectively with the selection of 2.7 volt from Vishay Zener diode like this one, we end up with this much of a variation of the nominal voltage of the Zener diode as a function of temperature. That is matching the variation of the nominal variation of the voltage of base emitter of BJT transistor as a function of temperature, which is on the order of same ballpark like this. So effectively, with this selection choice, Zener diode nominal voltage is tracking effectively the base emitter PN junction Zener diode, PN junction, let's say, temperature variation. So we sort of compensate for that by this selection of the Zener diode. Okay, so with that said, that's one reason that this 2.7 volt is a good choice for this circuit, let's say. The bias of the Zener diode is there via the 1 kilo ohm resistor. This is a two supply design circuit, so we have 12 volt on one side and negative 12 volt on the other side. So here we have negative 12 volt connected here, and because we have 2.7 volt, that means we are dealing with roughly on the order of, say, on the order of, say, plus minus 9.3 volt across this 1K. So what we are feeding through this 1K as a bias current for the Zener diode is naturally 9.3 milliamp. Okay, that's perfectly fine. So that is a very good, healthy current supply for the Zener diode to make sure it is far from the knee point of Zener diode and is perfectly on. So that's a good thing. Now, in this computation, of course, I made the assumption that we can neglect the value of the base current for the BJT transistor, which is true because with 2.7 volt at the base, so I'm going to write it here. This is voltage of the base is 2.7 volt. Then the VBE itself is 0.7 volt. So voltage of emitter of transistor DC is 2 volt. 2 volt across 2K will result in 1 milliamp DC current across this resistor, which keep continuing as a collector current for this one and will be effectively the emitter current for the main transistor T1. So I would say the DC emitter collector current of this transistor, or ICE, let's say, if you want to name it, but let's just keep with IC1, is again 1 milliamp. So that 1 milliamp going through 5.6K will result in plus minus 5.6 volt drop DC across this resistor. Given that we have a 12 volt supply, subtracting 5.6 will give us roughly for the voltage of collector VC for transistor 1 and 2 as well, T2 as well. So VC, or voltage of collector, equal to 12 minus 5.6, which will be 6.4 volt. Okay, so we found that the voltage of collector of these transistors is 6.4 volt, which is a very good choice for this design. Now we're done with the DC analysis. The nice thing is when the input voltage is 0, in the sense that we connect the positive terminal to ground, let's say negative terminal of the input to ground, then there is basically a 6.4 volt connected to the negative input terminal of the op amp, and 6.4 volt connected to the positive terminal as well. And naturally, in that scenario, without the presence of, let's say, AC voltage or varying voltage or non-zero voltage, then output is just 0 as expected. So V in 0, output is 0. So nice. Okay, so what happens now when we have some non-zero value? For example, when we, connect some, let's say, voltage between these two nodes. Let's see what happens. Okay, as a result, what happens is there is a bias, let's say, I base current flowing through the base of transistor T1, assuming we are talking about, so it's important to make sure that this is the case. We're talking about matching bipolar junction transistors here. So T1 and T2 should be matched transistors so that they are on the same substrate, they are on the same, let's say they're in the same package, they benefit from the same junction properties and thermal properties. So basically they have the same saturation current. So from considering the Shockley p-n junction equation for IV equation of the, let's say, BJT transistor, we have the current of the collector is equal to saturation current, and then e to the voltage of base emitter divided by thermal voltage VT, which is roughly 25 millivolt at junction at room temperature. So with that said, there is given the matched transistors, this current IB going into this transistor, and effectively that current is coming out as well. And then as a result, because of this applied differential voltage. So I'm going to remove this 1 milliamps because we already discussed that. So I would say I collector DC is 1 milliamp. That's what we found earlier. Okay, so now we are adjusting the current by applying this differential voltage. So this is a differential voltage that we are applying at the input of the circuit, Vn. Because of that differential voltage, as I said, I base, because of this differential voltage, I base is flowing into T1 and coming out of the base of T2, effectively sort of counteracting the quiescent, let's say, current, which is 1 milliamp. So, of course, this I base is in a way that the resulting current is considerably less than 1 milliamp, or we're not basically getting more than 1 milliamp. So let's see what happens. We have, let's do a, let's say, a small signal analysis here. So what we have is from the positive terminal, flowing through a 470K, we get to the base emitter of a T1, and then we get to R1, and then we get back to, say, 470, and then the negative terminal of input. So that's what we are seeing here. Okay, so let's just quickly write. I'm going to do it this way. So let me just open up some space here. All right. So what I'm going to do is I'm going to just do a quick AC analysis here, and I'm going to shift this portion, let's say here, and that would be fine. Great. That was about the Zener diode. So let's do the what we are seeing from perspective of Vin. What we are seeing from perspective of Vin, so we have, let's say, Vin applied. Let's say the Vin is applied at the input of the circuit, and we see 470 ohm. Then let's reflect everything from the emitter side, including R1, to the base side, AC analysis. And these are transistors that they're, let's say, small signal, so a small current. We're talking about the gain of the beta of the transistor to be much larger than 1, say, for example, at least 100. Okay, so with that in mind, I can say I'm dealing with 2 times, so if you want to write it like that, 2 times 470, because we have 470 here and we have 470 here in the return route. And then we have 2 times the base resistor HIE for the transistor if you're doing the AC small signal analysis. So we have, let's say, HIE of the transistor, but 2 times because we have 2 T1 and T2 transistors here. And that HIE, of course, is observed from perspective of base. So I'm going to just basically say 2RB, and that's another name. We can say 2 times terminal voltage divided by the current of the base. So that's the value of this resistor, 2 times RB. And then we have the R1, which we assume it's more than 1 kilo ohm for practical reason. Say a resistor between 1 kilo ohm and a few hundred kilo ohm, say 200 kilo ohm. And then we have the R1 reflected to the base from emitter, which would be beta plus 1 times R1 times, and it's just 1 R1, so we don't have twice, and that goes back to the negative terminal. So this is the scheme we have. If R1 is going to be more than 1 kilo ohm, then we then multiply it by, let's say, at least 101, because that's beta 100 plus 101. This resistor value effectively is equal to, we're talking about 101 kilo ohm. So this 2 times 470 is then 940 ohm, which is completely negligible compared to the 101. And then let's look at the 2RB. So it's, as I mentioned, this is 25 millivolt, the thermal voltage at nominal, let's say the room temperature PN junction. I base, well, we found the 1 milliamp DC bias current. Of course, I base is, so the I base of transistor is I collector divided by beta, and I collector is 1 milliamp, so therefore I base becomes 0.0 and 1 milliamp, 1/100th of that. Okay, with that, with the I base being 0.01 milliamp or 10 microamp, then what we get is 2.5 kilo ohm times 2. So effectively the resistor we have here would be just 5 kilo ohm. So in summary, I can say that let's say even if we consider beta more than 100, which is usually the case, but then I can say that the current that flows through the base because of Vn, it can be computed by Vn divided by 2 times 470 ohm plus 2 times Vt over I base and plus beta plus 1 times R1. So effectively, this is approximately, given that this is 5K, this is less than 1K, and you're talking about this one at least, with the minimum of R1 being 1K, actually preferred to be larger. With that, we can say this is approximately Vn over just beta R1. So that is the current of the base. Now, that's the current of the base that is generated by this input voltage Now, naturally, the current of collector is beta times that. So the collector current flowing like this, so will be beta times I base. Therefore, I get collector current is just V in over R1 because of beta in denominator goes away. Okay, so let's keep this. Now, the interesting part comes into picture because what we have is there is a collector current that is going through the 5.6K, as I just mentioned. So let me just do it this way. So there is this collector current AC that is flowing through this T1 because of the V in that differential voltage that we applied. This IC1 is the one we computed. At the same time, this IC1 will flow like this and go back AC-wise like this. So that's IC1 flowing. All right, so I need to make it, so that is the scheme about these two transistors, but the fact is this IC1 cannot go through the 5.6K. That's the nice thing about this circuit. So what happens is, effectively, this IC1 can only go like this. So it can only go through this branch, come down. So this is the IC1 we just talked about, and then go through this branch and then downward through this resistor IC1. So what happens is, since we apply the, let's say, proper supply voltage negative 12 volt and 12 volt to this op amp, and since op amp has a negative feedback output connected to input negative terminal, so op amp is operating in linear region, not saturated, it will enforce via negative feedback. It will enforce the virtual short, meaning that voltage at the negative terminal and voltage at the positive terminal, they should be the same. This is virtual short enforced by negative feedback of op amp. So what happens is then, effectively, virtually you can say these two nodes are connected together. So if the voltage drop here is R1, this has to be R2. So if the voltage drop here is R2 IC1, then the voltage drop here is also R2 IC1. And so at the output of the circuit, the total voltage with respect to the AC ground is R2IC1 plus R2IC1, because as I said, these two nodes are effectively virtually short together. And then, therefore, output becomes 2 times R2IC1. That's V out. So I can say then V out is equal to 2 times R2 IC1, but then using equation 1, I can say V out is 2 times, and then we have R2 substituting for IC1, V in divided by R1, we exactly get what we wanted. So I can just say V out over V in, or the gain of this differential amplifier circuit or instrumentation differential amplifier is 2 times RT2 over R2 over R1. So this is an important outcome. The part that I mentioned, the current cannot go through 5.6 volt, 5.6 kilo ohm, is because this is a op amp that is enforcing the virtual short between the two input terminals, as I mentioned. So they have to be equal to each other, the voltages. Now, if I go back to the current is a differential current. So if any portion of this differential current, if it is supposed to go through IC1, it will cause a voltage drop like this, if it was supposed to go there. And if any portion of the returning IC1, if it's supposed to go this way, it would result in a drop that is with a polarity that is the other way. So like this. So any portion of IC current flowing through this 5.6K branches connected to 12 volt will result in disruption of the voltage equality between the or virtual short between the positive and negative terminal, because one of them is trying to reduce the, let's say, negative terminal. The other one is trying to increase the positive terminal, for example. So therefore, differential current cannot go through these two 5.6K that has a common connection And then on one side they are connected to 12 volt. On the other side they are connected to, see, on the other side they are connected to the negative and positive terminals of the ideal op amp with negative feedback that enforces that these two nodes are the same voltage. So basically 5.6K, they have the same voltage drop across each other, matching. So therefore, no differential current can flow through these two guys, and the green differential current can only go through the route I am showing in the circuit. Practically speaking, it's important to make sure just to have the symmetricity in the circuit. It's important that these two resistors and these two resistors are, I mean, the 2K and 5.6K are matching to a very good extent practically. So at I would say an accuracy for these resistors on the order of 1% resistor or better is highly recommended. So if you can go, for example, even better than 1% accuracy when you select these resistors, those are recommended as well, aside from the fact that these two bipolar junction transistors need to be matched transistors. I hope this example is helpful in terms of showing one example implementation of the instrumentation differential amplifier using combination of 4 NPN bipolar junction transistors, 2 of them being the core of the differential amplifier, and then one op amp as the last portion of the instrumentation amplifier, computing the difference between basically converting effectively. This op amp is working as converting current to voltage in a sort of a differential fashion. And I hope that this example is helpful in terms of showing how this can be designed. Thanks for watching.